Good morning. So as Alex mentioned, that I've been working on system performance for many years. When I first started doing that, it was actually in Seattle. I graduated from University of Washington here, so it's really nice to be back in the same city. I learned a lot of stuff. And since then, I joined Intel in Oregon. I worked there for about 20 years. That's the time that I realized how hardware can help or hurt software performance. While I was working at Intel, I spent a lot of time working with other software companies that is looking for ways to improve their software applications running on Intel systems. And during that time, I was very fortunate to work with companies like Appeal, BEA, Sun, Siebel. So I mentioned these four companies. I wonder, any of you have heard about these companies? Have you noticed a pattern about these four companies? They are all acquired by one company eventually, that's Oracle. So for the last 6 years, I was in America. I had been working with Oracle to speed up Oracle software performance on Intel servers. And most of the work is around middleware, Java applications, and sometimes cloud computing. So at that time, I was wondering, what should I be doing? So while I was working as an Intel engineer working with these companies, I could do a lot of analysis, but I could not change the software. The software belongs to those companies, and I may not even access some of the components I want to study. So I was thinking about, it would be great if I can work for a company that actually occasionally allow me to change some source code. So I was looking around, and Alibaba gave me a choice. They say, well, come over, figure out what problems we have in Alibaba, and do something about it. That is the job description. So I hope many of you would like that kind of job description. And I took that. So I moved to Alibaba in Hangzhou, China, about 2 years ago, thinking that I would be doing exactly that. Of course, once I went on board, I need to deal with other issues. But I'm not going to bore you with the other issues. I'm going to stay with the interesting thing that is when we look at the performance of a large number of systems, what kind of interesting problems we observe, and what can we do about it. I want to call out a disclaimer here is all the data here is not real data. We modify the data slightly so that we can tell the story. And also, the talk today will compose of a lot of graphs and data. At any time, if you have a question, please ask at that time. You don't need to wait until the end of the section. That will make the discussion easier. So here's the journey. We are looking for ways to improve the performance. For us, improving performance means that we can do more with less. But I want to put the problem at scale so we can all see the things differently. What we are talking about here is we have a large number of servers. I make up a really big number that is not a real number, okay? So 1 billion servers is way more than what we have. But I want to give you a sense of the scale of the problem we are facing. And I was told I cannot give the exact number, so I just went with that. But the most important thing about the number of servers we have is we are looking for a 1% performance gain. If you have a 1% performance gain across all the servers, it is a very big number. So we're going to talk about when we are looking for that kind of a small performance gain in terms of percentage, but in terms of number is a big number, what kind of data we are looking at and what kind of problems we face. And more importantly is once we have all the data in front of us, we are studying the data, we need to make some decisions. And because of the scale of the problem, if we make a wrong decision, it's going to cost a lot. And hopefully we can make all the right decisions. And on the way to make all the right decisions there, we are encountering issues. I would call them potential mistakes. And how do we discover mistakes? And how do we go around those problems? So I want to talk about performance in the small and performance in the big. So on the left side there, I guess the, does it show up? Oh, I just don't know how to point. Okay. All right, so we spent a lot of time while I was with Intel is we run small benchmarks and we study the performance impact of these benchmarks. Then we try to scale the performance of the small benchmark to a very large systems. If you have a benchmark that is stable, everything works very well. But the reality in our large data centers, and for most companies, is the software changes all the time. Sometimes the software changes every 2 weeks. So by the time you try to scale the performance of any benchmark into the data center, it may or may not work well. So we're constantly dealing with these things. Can we use benchmark? And if we don't use benchmark, what should we do in a large data centers? Now, stepping back here is when we have a large data centers, the performance of a single software system may or may not be the most important factor. So here's a paper that was published a few years ago. On the right side is the paper that was published by David Lowe from Stanford. So he studied 2 data centers a few years ago. And on the left side is one company that starts with T. On the right side is another company that starts with G. And he looked at the utilization of the systems. At that time, he found out that it's roughly 20% to 30% CPU utilization. What that means is we spend a lot of money buying the CPU, but we use only a fraction of the CPU. So how can we make use of more CPU? That is the question. But what I want to point out today is we are going to look at what the CPU utilization by looking at the process we have been thinking about solving a problem. CPU utilization is one of the metrics to measure the utilization of resources. There are other ways to measure the utilization of resources. While we are looking at the problem, we want to break down the process into 3 components. The first component is, can we really measure what is happening right now? How confident are we about what that is? So that is on the left side there. What is happening right now? The next question is, what can we do to make things better? Now, when we talk about what we can do, we are not talking about changing a single line of source code. We are not talking about changing the scheduling. We are talking about anything, including changing the software, replacing a rack of machines. So how do we determine whether that is a good thing or bad thing or how good that is? So we evaluate that, and on the right side, we need to make a decision. Is it a good thing to do? And once we make a decision and deploy in large scale, we study the effect, whether it is worth it. If it is a software change, we can roll back. But if it is hardware change, it will stay there. So for anything that involves a hardware change, we want to be very careful about it. Now, Alibaba and many companies have a lot of engineers. They are taking a lot of telemetric data. Actually, I was surprised to see yesterday there was a slide about an elephant as well. I think he had 4 people studying the elephants, but I have 6 people. That's the only difference. So you have engineers trying to study the systems. They pick up data like CPU utilization, memory utilization, maybe task switches, counter switches, network interrupts, a bunch of stuff. And all these data are coming in. And every one of them is going to tell me that I am studying the most important metric. I want to use the metric to drive the decision. However, everybody is looking at a small piece of the problem. But we still have the ultimate problem to solve is how do you study all different kinds of software running on many different kinds of hardware in the data center? We are not talking about the PUE, studying the power utilization of data center. We're talking about real software doing something in the data center. Can we unify the study of the optimization of such a problem? So here's the first equation. This is a very simple equation that we're thinking about. Maybe we have a solution. What we are talking about is something we call resource usage effectiveness. For every piece of work we need to do in the data center running some software, the software is doing something. The software may be doing a batch processing. They may be processing some big data operations, map reduce, or the software may be doing something like the e-commerce applications. Speaking of e-commerce, have you heard about Singles Day in China? Anyone heard about that? Good. Only a couple of people. Yeah, it's a very busy day. It is going to load up the a lot of the network activity. Let me talk about how big that is. On the Singles Day last year, 2018, November 11th, we generated sales of, if I remember correctly, is $30 billion US of merchandise. $30 billion. How big is that? It's more than Thanksgiving, Cyber Day, Boxing Day combined with change. So on that day, we need to handle a lot of traffic, and all the systems need to run. We need to do 2 things. One is we want to satisfy all the requests when people are shopping online, doing a bunch of stuff. We also want to make sure that we provision the right amount of resources. And because of that, we pay attention to the software efficiency. So this is a very simple equation. And can we actually do that across a lot of different software applications? The equation on the top, we call something called resource usage. Somehow, we should be able to measure the utilization of some kind of resource. I gave several examples of the resource at the bottom there. So CPU, memory, storage, and network. For some of you in the room here, can you guess what are the 2 most expensive components in the data center across any company? The answer should be the same, more or less the same. Sorry? Air conditioning for power, yeah, that's true. But I'm asking you to pick 2 out of these 4. Yeah. Network bandwidth is expensive, yeah. And when you buy a server, right, the server is composed of 1 or 2 CPUs and some amount of memory. And sometimes the server comes with some storage. And if the server is specialized for storage, then storage will be expensive. If you are buying a network switch, of course, the network component could be expensive. But in general, when you look at all the servers in the data center, most of them are computing something in response to user requests, or they are being used to do something about the favorite topic here is AI and machine learning. They also compute a lot of CPUs. And while these applications are consuming CPU, they use memory for temporary storage of whatever objects they need to store. So in many data centers, CPU and memory are the expensive components in a server. And today, we are going to pick CPU as a component to study the utilization. So we pick up the resource usage, and we need to deal with the second thing is how do we measure the amount of work that is being done in the system. Because we have many, many different kinds of applications, they are measured in different ways. We want to unify them in some simple terms so most of the people can agree that it is a good thing to do. So we look at some of them, we call them queries. You can think of queries as the transactions happening on a server, like you are shopping online, you go to Amazon, you put some item in the shopping cart, then later on, you decide that you want to buy that thing, then you execute another transaction. So there are a bunch of queries happening in the servers to process these things. And when you're doing something like machine learning, big data operations, you have some tasks that are processing maybe billion model. So we come up with this equation, and we hope that is useful. And at this time, we're looking at the misleading behavior of CPU utilization. So here I want to be a little bit generous to CPU utilization and ask a question. Has any of you looked at the CPU utilization of your workload running in your data center? Probably many of you have looked at that. How much do you believe what you are reading is what you think you are reading? Thank you.
But that doesn't tell the whole story, because if the load is unbalanced, you might have next to nothing on one node and 100% on the other.
Exactly. Yeah. The node might be unbalanced. So you have 0% on one, 100% on another. What is really interesting is if you look at how the OS kernel is computing the CPU utilization, is they use a specific formula, and that definition is what they use to produce the CPU utilization. I'm going to get back to that, but to illustrate the problem of looking at CPU utilization is, I want to pose this question to you. Given that you have a data center, a large number of servers, and across the board, you are using 50% of the CPU. And we also assume that you don't have load balancing problem, no software scaling problem, no interference problem. Of course, those problems are real, but to simplify the problem, we're saying that, well, let's assume that you don't have those problems. Everything's scaled, everything's perfect. We are just focusing on the definition of CPU utilization on a server. So naturally, some people might think that, well, if I'm only using 50% of the CPU, then I should cut it by half. Anybody agree with that? I need at least one person to agree with that. Thank you. Okay. So I'm going to go straight into what some of the CPUs might be doing to help you. And while they are doing something to help you, they actually cause some misunderstanding of some of the numbers that are being generated. By far, right now, most of the CPUs used in data centers are Intel CPUs. So I'm going to focus on that. And Intel CPUs, this is not against any CPU or supporting any CPU. But what I'm calling out is if a CPU has a feature that is similar to Intel that is called hyperthreading, and some of you have heard about that? Good. Hyperthreading is a system to make your software run faster. It is doing a lot of good things. In this example is on the top there, when you have a thread running on a CPU without hyperthreading, the thread will just consume the core of the CPU, and you will proceed. And if the thread is stored or cannot use all the resources, then you will slow down the utilization of CPU, in a nutshell. Anybody from Intel here that can correct me? Okay. With Intel hyperthreading technology, that has been around for more than 10 years. So when you have two software threads running, and these two software threads can be placed on two hardware threads. And these two hardware threads are running in parallel. And they are consuming a single core, but with some tweak in the CPU, Intel make the core appears as two logical CPUs to the software threads. So the OS does not need to change a single line of code. The OS can place all the software running on the same core. Everything is running fine. And the next picture illustrates how the efficiency is improved. So on the left side, you can see that without hyperthreading technology, the black software thread is using some of the components of the core. And the green software thread running on the green hardware thread is also using some of the resources of the core. Because these two separate cores without hyperthreading technology, they cannot overlap. And with hyperthreading technologies, these two software components running on two hardware threads are sharing the same core, so things are faster because they can use the resources more effectively. Now, all these things are happening behind the scene in the data center. It's happening every day right now. And believe it or not, many of you have laptops, and most of your laptops actually have hyperthreading technology. So for some of you that have the laptop open, you can open, if you're running on Windows, you can open perf. You can see that you have, even though you pay for 2 cores, but 4 CPUs show up. And that is the reason. Now, these virtual CPUs are bringing performance improvement. So that is good. This is the example that if you happen to have a laptop with 2 cores, and they will show up as 4 logical CPUs. And when you look at the for windows of performance numbers there, the charts there, you see that these 4 logical CPUs have varying degree of utilizations. The only thing we need to remember is these are not 4 real CPUs. These are just 2 cores that behave like 4 logical CPUs. So we need to keep that in mind when we study CPU utilizations. So now let's get back to the 50% CPU utilization. If you have 2 cores running at full CPU utilizations, that is the picture on top there. So each core is using 100% of the hardware thread and running some software, and it's 100% utilized. So that 100% is reliable if you don't have hyperthreading turned on. However, in the data center, to get the optimal performance, hyperthreading is usually turned on. If you go to any cloud providers, you subscribe some resources. Sometimes they let you subscribe a number of, they call vCPUs, virtual CPUs. So we want to compare two scenarios. And in these two scenarios, they both show 50% CPU utilization. Let's see what that means to you. On the left side, we have hyperthreading turned on. That means we have two cores that appear as 4 logical CPUs. And within these 4 logical CPUs on the left side, 2 of the logical CPUs are fully utilized. 2 fully utilized CPUs divided by 4 CPUs, so we got 50%. 2 divided by 4 is 50%. We agree on that. On the right side, we also have a similar scenario. We have 2 cores. They appear as 4 logical CPUs. On core 0, on the left side, the 2 hardware threads are fully utilized. On the right-hand side, the 2 hardware threads are not utilized. This is a very simplistic picture to show that on the left-hand side, we are utilizing 50% of the CPU. And on the right-hand side, we are also utilizing 50% of the CPU. The question is, are these two 50% utilization the same or different? With the picture I'm showing here, you can probably see that they are different. How different are they? That's the question. Now, why does it matter to you? If you just run some piece of software, you're looking at the utilization, what do you get? Do you get a picture about the utilization across all the logical CPUs, or do you just get the final number? The answer is, most likely, you just have the final number. And it will take you a lot of effort to figure out exactly which scenario you are in. So in summary, what we are saying here is when you just have one number about the CPU utilization, it may or may not be what you expect. So now you may be wondering, if this is a real problem, how come it is hardly mentioned in a lot of presentations? Do you guys have that feeling? So we run some experiments. In fact, you can run these experiments on your laptop. So if you are curious whether this is really true, you can follow the same procedure here and do some experiments on laptop, and then you will see that the performance numbers, you will see the performance numbers and the phenomenon like what we observe here. For our experiments, we don't use laptops, we use servers. So we use Intel Xeon CPU with 2 sockets, 2 CPUs, and each CPU has 16 cores per socket. And we turn on hyperthreading. This is a very typical scenario. We run a server in a data center. It's not just we. Many companies are doing the same thing. Now, to illustrate this problem, we pick a benchmark so it is easy to see where it is coming from. We pick Spec JBB 2005. If you have a Spec license, you can download it from the Spec website. The good thing about this benchmark is each warehouse, the component running within this benchmark, will run on one logical CPU. So we can distribute the warehouses based on how we want to distribute on the logical CPUs. There are many ways to run the benchmarks to make things easy. We only run 2 configurations. One is we run on half of the logical CPUs. So if you have 4 logical CPUs on your laptop, you run on 2. In our case, we have a pretty good server, so we have a total of 64 logical CPUs. In our case, we run on 32. And then you'll compare that with running on all the logical CPUs. So in our case, it would be 64. So we just look at these 2 simple configurations. Now, this is the experimental result. I will go through this slide very slowly so we can all understand what we are seeing. On the left side, is when you're running this benchmark, you get a throughput number. The throughput number is like one of the things we talked about earlier is the transactions per second. Here we call it MOPS, million operations per second. On the left-hand side, we are running on half of the logical CPUs. We are doing about 1.2 million operations per second. We are only running on 32 logical CPUs. For the red bar, we are running on all 64 logical CPUs. We are using everything. We are doing about 1.2 million operations per second. That means we are doing about the same amount of work between the red bar and the blue bar. On the left, we are running on only half of the logical CPUs. So that is the top chart on the right here. So when you're running on only 32 logical CPUs out of 64, and everything is utilized, what do you get? 50% CPU utilization by definition of OS. Out of 64 logical CPUs it can access, 32 is very busy. And because this is real data, so I actually have a small error there. I got 50.16, so sorry about that. It's slightly more than 50%. And because it's real data, I got, for 64 logical CPUs, I actually got 98.59%. So, but essentially, they're close to 50% and 100%. But it's very important to notice that the 50% utilization is doing about the same amount of work as the 100% utilization. And that is the key metric we are going after. When we are consuming CPU on the systems, are they doing useful work? In our case, when they are generating operations per second, they are doing useful work. So now we are puzzled. What exactly is going on? 50% of the CPU utilization or 100% of the CPU utilization is doing about the same work. So we check one more thing. The next thing we're checking is the number of instructions that got executed per second. These are the machine-level instructions. These are the instructions that are something like your software is compiled to some binary code, and the binary code is loaded to memory, got executed by CPU, and some of the instructions are executed repeatedly. So it's the dynamic count of the total number of instructions. And not surprisingly, when we look at the dynamic count of the instructions per second, they are about the same. So in a nutshell, what we are showing here is when we turn on hyperthreading, the CPU utilization is distorted. Now, this is the extreme case. This is distorted by almost 100%. In some other cases, maybe they are OK. But a maximum error of 100% is what we are seeing based on this example. The real problem is actually a little bit more complicated, but we won't go into that today. The real problem is when you are dealing with the CPU frequency that may change during the run for power saving. So now what we got here, I hope some of you will agree, maybe what we have been looking at as CPU utilization is not exactly what we are looking at, even though the OS will define it that way. It is not about the capacity we are consuming. It's about some math that is generating the number for you. So right now, I want to show you two examples about some of the symptoms, some of the mistakes that some of us might have made. While on the way to get the data we need on the servers, we produce tools to get the data. when we have engineers developing the tools, the typical thing I hear from the engineers is my tool has zero overhead. You guys have such engineers in your companies as well? My tool is perfect, doing everything right, no problem. And they show me the data. Look. I run 2 experiments. Experiment 1, I'm doing 9,520 operations per second. I put my tool there. I got the same throughput. So my tool is perfect, no overhead, everything is fine. I'm glad that you are shaking your head. So there are other things that are happening on the system. And one of the things we mentioned earlier is the CPU utilization. Maybe the tool is introducing something that consumes resources. The resources could be consumed in memory, CPU, many other things. What we are showing here is if we ignore other metrics, we may have a distorted picture. This is another example while we are doing the JBB experiments. And maybe some of you are running some software, especially if you're running software on the JVM, is when you're running software on a Java virtual machine, the JVM can be configured with many parameters. And sometimes the default parameters got changed. In this example, even though they are running the same 48 warehouses, we are observing that the throughput number is significantly reduced. Then the engineer will say something like, I didn't change a single thing, so it's not my fault. But is it possible that running the same software on the same JVM, there can be such a huge performance difference in terms of throughput? So when we get around to get the data, we realize that the Java virtual machine was configured in a different way. And because of the difference in configuration, the performance dropped by about more than 20%, I believe. It's something about a special feature in the JVM. So if you happen to be running Java applications in the cloud or in data center, and if you are crossing the 32 gigabyte boundary, you may want to pay attention to that. And if you usually run your heap way less than 32 or way more than 32, this is not a problem for you. But because it's a Java feature, so I won't go into detail here. What I'm showing in the last 2 examples is we need to look at the resource utilization data to figure out something. We also need to understand the throughput can be changed by some configurations. So what does that mean? To summarize, what we are dealing with is the early example of just showing CPU utilization may not be adequate for me. So we look at the published papers, and especially the papers relating computer architecture and software performance. And many professors and many PhD students have written about this iron law. This iron law is a way to break down the efficiency of your software into 3 components. On the left side, we are looking at how much time we need to spend to do a unique amount of work. So we can do a lot of things there. But to help us to think about how we can divide the work into components, we'll break it down into 3 things there. The first thing is for every unit of work, whether it's transaction, big data operations, how many dynamic instructions you need to execute. That's the first component. We call it path length. The second component is the number of cycles we need to execute per instruction. Now, the number of cycles refers to how many clock ticks you need to execute on a CPU. and you divide that by the number of instructions. And that is called CPI. And the third component is about how much time you need to take per cycle. So these are the three components that can help us to think about software performance. As always, when we have a formula about software performance, we take it with a grain of salt. This is just a way to help us to think. It has some limitations, but it is a very good starting point. Among these three things, the one thing that pops up in a lot of the presentations is CPI. The reason is, if you look at the left side, the number of instructions you need to execute per unit of work, right? Everybody is doing different software, so they have different number of instructions per unit of work. It is hard to compare. And on the far right side is among the execution time per cycle. So if you buy a CPU, it's running at a certain fixed frequency. That's the maximum frequency you can go. So there's not much you can do on the right side either, except that if you can pay more money, you can get a faster CPU. What's interesting is the middle piece as a CPI. In fact, this piece is so interesting that both Microsoft and Google has published some papers about how they use that to help with the performance tuning. If you want to shorten your time of your program, you might want to reduce the cycles per instruction, right, based on that formula. Recently, a Netflix engineer called Brandon Gregg, he has published that, well, CPI. So for many of us, we don't know much about CPI. What is a guideline? What is a good CPI? What is a bad CPI? So there are lots of different opinions about that. But we all agree that if we can reduce CPI, it's a good thing. Any of you have looked at that? No? That's good. That may or may not be needed. If you are running exactly the same workload as before, then the instruction mix will be exactly the same, and CPI will be a good indicator. If your software is changing every 2 weeks, then CPI is a little bit hard to handle. Now, let's say we are lucky. We are running the same piece of software. And I bring up my favorite example, Spec JBB 2005, that is relatively easy to run. I want to pose a question. Once you have bought a piece of hardware, are the default hardware options already optimized for your workloads? Before I go there, I want to ask a question. Once you buy your computer, have any of you played with the BIOS options there that can change the settings of the CPU? Hey, thank you.
We do a lot of work playing with all of the options before we set things up. And you get very different answers and results.
Yes, exactly. Thanks for sharing. So you can get very different results based on the BIOS options. And the number of BIOS options on a server is way more than your laptop, right? Yeah. So they have, like with the current CPU, they have 8 prefetches. They have different ways to do resource-directed technologies, many, many options. So when you are dealing with that, a CPI comes in handy. When you are tweaking these options, it will be helpful to check, are you reducing the CPI? Is that right? I hope you agree. Yeah. So that's what we check. And the other thing we want to check is, even if the hardware options are not optimal for our workload, it's probably close enough. Maybe a few percentage of the optimal point, we are OK. And in this drastic example running on Broadwell servers, that Broadwell server is about 2 years old, we are seeing is there could be a 25% performance difference running the same software by tweaking the hardware options. The hardware options are setting or not setting NUMA. And also, along with the hardware options, NUMA control is you bind the software process to a NUMA node. And also, a COD is a special feature called cluster on die, is breaking down a single socket into 2 nodes that can process things efficiently for you by reducing the memory access and improving the cache efficiency. Now, all these are really cool stuff that each of you probably has a special hardware engineer that deal with these things for you, right? So what we got here is when we are turning off everything, by the way, turning off everything is not the default. We get a performance of 293,000 operations per second. We call that the baseline 1.00. When we turn on everything, we got 366,423. So the overall speed up is 366,423 divided by 293,627. We got 1.25. This 1.25 increase in performance, a good question? Why it's not a default? Because Intel actually, good question. Intel actually has a recommended default when they work with different vendors. So if you are buying your servers from different vendors, they will implement some set of default values for you, thinking that they know what you're running. And if you like, you can go to the BIOS of your server computer. You can check what they set. Now, there's another interesting thing is about these vendors is sometimes they pick a default for you. They don't expose that to you. So you don't know what they set because they thought they already fixed it for you, so you shouldn't need to know. If you encounter that problem, you can go through a convoluted way to get the data by looking at the MSR register. If you're curious about that, just send me an email. I'll send you the documents. Now, because because turning off everything is not likely the best option, so some of the options will be turned on, but the options that are turned on are not these 3. The options that are turned on are the related to the prefetching of data through the CPU, the speed of the memory. They're not these 3 items.
So there's way more options. There's way more workloads.
Wait, sorry?
That's maybe suboptimal for different workloads.
Yes, exactly.
At some point, I want to ask. Yesterday we heard, and we have had this pain where we can measure in a controlled environment for this benchmark something. And in real life, through telemetry, we observe something else not unrelated to that something we measured in the synthetic test. But I was wondering if there are, I was wondering if, there is room for either here or offline to exchange some insights about that.
They're actually to my next section.
Perfect.
Thank you so much.
Awesome.
So I want to address the comment there. Yes, different workloads may require different optimizations, and that is a challenge we face. Can we set one set of hardware optimization for everything? Or can we get the CPU to study the workload so it can self-tune itself? And for some of the self-tuning activities, some companies will be driving it from the hardware point of view, and some companies, like the software companies, they would like to look at it from the auto-tuning from the software point of view, like the work done by MIT called OpenTuner. You can try it. And also there is a work done by Twitter about tweaking the JVM parameters for their operations, processing tweets. So there are many different options, and this is the area that machine learning may come in handy to help us to auto-tune some of the workloads. But with that, I want to go to the next section. The next section is exactly what you mentioned. Is, well, we have a lot of different things, and things change. And how do we do that in the data center? So we think that, well, if you have a lot of different workloads running in the data center, you have a large number of things. So hopefully, the average behavior, we have the extreme cases canceled out. So hopefully, we can do something about it. Now we need to come up with a way to evaluate if we are doing something better or worse. We call that Speedup. The definition of Speedup is consistent with Patterson and Hennessy, who won the Turing Award last year. This is a version derived from their textbook, Quantitative Computer Architecture Performance. So the Speedup is essentially the RUE of the base case divided by RUE of the new configuration. So for the base case, we call it configuration 1. For the new configuration, we call it 2. So we take the speed-up ratio of these two numbers. But we want to apply it to a very large number of servers. And we need to deal with the operation difficulty of distributing a lot of software applications on a lot of servers. So at this point, we cannot have a very precise setting, like what you said. We are going to deal with some fluctuations of data. And we hope to be able to make sense of the data and still make some decisions. And the key thing you want to remember is, for speed up, the bigger the number, the better it is. So here is a scenario of the problem in the data center. Everything is live. We put on a lot of stuff. We want to test a new feature. The new feature could be updating a software, like updating OS, or updating a virtual machine instance, or changing some hardware, changing the configuration, something. We cannot afford to change a lot of things during testing. We can only change a small number. A small number is a big number in our case, but it's 1%. So 1% of the instances will be running on the new configuration, while 99% will be running on the old configuration. Everything is live. They process a lot of transactions. They process real stuff. For this experiment to be conducted, we need to have fair confidence that nothing really bad is going to happen to the 1%. So we have done some testing to make sure that it cannot be too bad. You cannot crash 1% of the servers. We'll be in big trouble. And we cannot ask many other teams to change the way they work. Like if there is a scheduling software distributing the applications on a large number of clusters, they will just schedule the way it is. So no change in any team's work. The only change is 1% of the machines will get a new configuration. And also remember one thing is many software will be running on the same server. The same server is running many applications. I think I have a picture in the next slide. OK, so this will help a little bit. In this picture, we are showing that we have 4 servers. Machines 1, 2, and 3, and 4. Now, the top 3 machines each has about 4 cores, and machine 4 has 6 cores. So machine 4 is wider. And some of these machines are running different number of applications. On the top, machine 1 there, they are running 4 different applications at 1, 2, 3, 4. And it just happened that due to the distribution of software, 2 applications are running on machine 2, and another 2 applications are running on machine 3, and 4 applications with different amount of cores assigned to each of them are running on 4. So we make a change to the systems. And when we make a change to the system, we don't control exactly what system get picked. Somehow, some systems got picked. In this case, we make it simple. So machine 1 got picked. Machine 1 got the new configuration. And all the software applications running on machine 1 are running on the new configuration as a result. So in this case, it's a hardware configuration change. And all the other applications are not affected by the change. So what is interesting here, I want to really call out here, is we are not comparing before and after. What we are comparing is, on the right-hand side here, We have some machines that are running the old configurations, and we have some machines that are running the new configurations. And all these machines are running a large number of software applications, processing a large number of transactions, and hopefully they are all doing about the same thing. So we have a fair amount of uncertainty there. But the reason we have this, we allow to have this fair amount of uncertainty is we want to make life easy for a lot of people. They don't need to change a lot of things. We want to locate things we can deal with. We want to locate things that are helping us in performance. So this is our big data. You may look at the data and say, well, it's small. Yeah, it's small, but it's from a large number of servers. So we have this study. Again, this is a hypothetical example. We are looking at a change in the configuration. 99% of the apps are running with configuration 1. And for the 99% of apps, we are getting RUE of 885. Again, RUE is resource usage effectiveness. The smaller, the better. So we are spending 885 resource units per transaction. And then we have some number of machines along with the software applications running on configuration 2, and they are getting 815 resource units per transaction. So we take the ratio of these two numbers, we got 1.09. This is a speed up. So we say, wow, somehow this change is really, really great. We improved the average performance by 9%. Are we going to do that to all the servers? That's a question for all of you. Why not? Yeah, why not try it out? Maybe it works. Good. But changing a large number of servers for this configuration change is very tedious. So guess what? The person that discovered this are going to push, why not? We should go for that. But then the person that is actually required to do the change with us, are you sure? Then we have another group of people that say, we need more data, but exactly what more data you need, that's the question. How do we break down the need of the additional data? Or the other way to think about it is this analysis sound? Yes?
It may not be a sound basis for changing all the processors because we don't know whether the load behavior on all the processors is the same. If you have an enormous amount of variation, then you could actually be doing some harm.
Exactly.
Large number law is not going to help you unless the population variance and mean are the same all the way across.
Yeah. That is one thing we check. Yeah. This is a good point. So when we look at a large number of data, we are just looking at one kind of workload. Even though we say these are all applications doing about the same thing, we have a question. Are they processing the same kind of transactions? Are people executing the same kind of transactions on this piece of software? In the case of Amazon, are we doing all checking? Are we all checking in items to the shopping cart, or are we doing search of items? Even though these operations are happening on a similar set of software, the behavior will be different. So if we drill down to the behavior, we need a lot of data. But asking for a lot of data will be very demanding for a lot of people. We want to find some compromise. We don't want to get too many people to do too much work, but we want to get some sense of how good it is. So based on the operations of the apps, we divide the apps into 3 groups. What is interesting here is once you look at the breakdown into 3 groups, on the right-hand side here, we are showing 3 numbers. For app group 1, we move from RUE of 1289 to RUE of 1484. For app group 1, we are increasing the utilization of resources for this whole group. And we are losing 30% of the efficiency, 13%. And then for app group 2, we do some similar computation. We're losing about 1%. It's not too bad. And then on app group 3, we're losing about 16%. And we call this big data paradox, leading to the next slide. So what we are seeing here is when we look at the overall impact, it seems very positive. But when we were able to break down into different components, sorry. Okay. Well, okay, I'm going to make it fast. When you break down into different components, we actually lose performance. Unfortunately, this is not something new. People have observed that over the years. Some of you might have heard about Simpson's paradox. Anybody has heard about it? This has nothing to do with Bart Simpson. So Simpson paradox, he published an observation in 1951. He said that sometimes we look at a trend, the overall trend is the opposite of the individual trends. So today I want to spend some time to explain, based on what we are observing, how did that happen. By the way, I apologize. I did not realize I'm running out of time. So if I don't get a chance to go through all the slides here, and if you're curious about how to explain this to other people, I'm happy to talk with you after the session here. So when we turn on the feature, I put the color blue there. So that is when this feature is turned on, and color green is when the feature is off, the default case. We are checking if the increase in performance is real, and we find out that the per group comparison will have a reduction in performance, while the overall performance is good. Now some of you need to get ready. You need to go back to your high school mathematics now. In this case, we are looking at, on the x-axis, is the number of trials we try, and on the y-axis is the number of successes. In other words, this is a success rate of different things. And when we are comparing success rate, we are comparing the slopes of the line. We are comparing the slope of blue line versus the slope of green line. In this case, the slope of blue line is better than the slope of green line, so there is a better performance. And in the interest of time, I'm going to skip these 2 slides, go to the last slide. When you are comparing the dark blue line versus the other, there's supposed to be green line, sorry about that. The dark blue line versus the navy blue line, there is a performance increase as indicated by the red-yellow. But individual comparisons, comparing the, looking at the far left red arrow and the far right red arrow, there is a decrease. So we need to correct for this kind of misunderstanding, or we try to avoid making decisions if this kind of symptom occur. So I just want to summarize the three big problem groups we try to avoid. The first thing is CPU utilization may be more complicated than it looks. And CPI is not simpler. The last thing is the average performance change from a lot of data might also be misleading. If all these things sound really complicated, just remember one thing. When people are taking ratio, watch out. If you really want to try your data analysis, we just published Alibaba cluster data 2018. We just released 2 months ago. And you can play with the data. If you decide to publish a paper out of it, like our 2017 data set, there are 5 papers out of the data set, and one of them got the best paper in OSDI. Because I run out of time, so I want to cut to this slide to summarize. Actually, not to summarize, to let you read about it. And if you have any question, I can address it here, or we can just go out. I will stay outside to discuss some other interesting problems, or you can share with me your experiences as well. Thank you.